Good day, everyone. My name is Ali Haydari, and welcome to this session. Today, I'm going to present our research titled In-Storage Processing of I/O-Intensive Applications on Computational Storage Drives. Please feel free to write or ask your questions, and I will be happy to answer them at the end of this presentation. A little intro about myself. I'm a PhD candidate in computer engineering at University of California, Irvine. I got my bachelor's in electrical engineering from Sharif University of Technology back in 2016, and my master's in computer engineering from UC Irvine in 2018. My research focuses on computational storage drives and distribution of processing over heterogeneous systems. My research is in collaboration with NGD Systems, where I've been doing internship for the past 4 years. NGD Systems is a startup company that specializes in high-capacity NAND-based storage solutions. We are proud to be the first company to fully develop computational storage drives at capacities of up to 32 terabytes. With the new trend in data generation, the total size of data has been increasing exponentially. In 2022, the total size of data in the world is about 80 zettabytes or 80 million gigabytes. In 2025, it is anticipated to go up to about 175 zettabytes. This increase comes from the new generation of technologies that creates massive data. Technologies such as IoT devices, healthcare monitoring systems, or autonomous vehicles. We also know that a great portion of data is meaningless unless processed in a proper way. That is another emerging challenge that needs to be addressed, either by deploying high number of processing engines or more powerful processing platforms, or by utilizing new methods to increase current platforms' performance. Three solutions to store data include tapes, hard disk drives, and solid-state drives. Tapes are out of the scope of this work, so we're going to focus on HDD and SSD. We believe SSD is a better option over HDD as it provides better performance. For instance, the read-write bandwidths of SSDs are in the order of gigabytes per second, whereas HDDs caps at about several hundred megabytes per second. In terms of latency, SSDs are 10 times faster than HDDs with latencies of hundreds of microseconds. SSDs are also more efficient in power consumption as there are no moving parts. For instance, in lower power modes, SSDs are almost off, whereas hard disk drives have to maintain a constant rotation to keep the performance. Comparing storage densities, SSDs can fit tens of terabytes of storage in a 2.5-inch drive, but HDDs cap at a couple of terabytes. Also, since there are no moving parts, SSDs are more durable in harsh physical environments. However, there are some aspects in which hard disk drives are better than SSDs. The most prominent one is the cost of production. Right now, SSD is about 5 times more expensive than HDD in terms of costs per terabyte. But this gap is decreasing, and flash production is anticipated to cost lower than HDD at around 2026. This reduction in cost of flash production is due to the new technologies such as QLC or quad-level cells and 3D scaling of NAND chips, which means stacking several layers of NAND flash in one package. Also, flash has a limited number of write cycles before being worn to a level that is beyond error correction capabilities. An enterprise-level flash can get up to 3,000 writes on a cell, but HDDs virtually have unlimited writes. Here is an additional chart that shows the number of SSDs and HDDs in terms of number of shipped product for the past years. As you can see, SSD is reaching to HDD in number of shipped product, but there is still a considerable gap in terms of shipped capacity that was mentioned in previous slides. A typical architecture for running applications is to load the data from the storage unit to the host processor or an array of GPUs to run the computation. Assuming to have a server like the one in the figure, we can have a raw bandwidth of 545 gigabytes per second out of the NAND flashes. But on the other side, based on the number of PCI Express lanes, we can have a maximum bandwidth of 16 or 24 gigabytes per second. This high-level example shows how communication can become a bottleneck, especially in I/O-intensive applications where there are a lot of data transfers and only a limited amount of computations. Examples of such applications are the embedding table lookups, where the entire table should be loaded on the DRAM, but the computation is a set of multiplications and additions. Our solution is to move computation engine to data to avoid heavy data transfers. We can do so by placing a processing engine inside the storage drive. Having a processing engine inside the storage drive can eliminate data transfer, which in turn helps better preserving privacy and security, and it obviously can help with the bandwidth mismatch that we saw earlier. In this work, we introduce a novel high-capacity CSD design. We develop in storage processing for CSD. We also develop a scheduler to run distributed processing, and we deploy distributed NLP applications on CSDs. As we've seen before, CSD tries to put a processing engine close to where data reside. There are three approaches to implement the idea. The first one is to share the current processing resources on the storage drive to implement in-storage processing, or ISP. This approach requires no significant changes in the hardware, but it only provides a limited ISP capability for limited simple tasks. It might also reduce the SSD performance under heavy workloads as part of the computation resources is being utilized somewhere else. The figure on the right shows the overall diagram of such designs. The second approach is to couple an external compute unit with the storage drive on the same board. Usually, a reconfigurable computation unit such as FPGA is chosen to provide high throughput. This approach is relatively easy to implement, but it does not consider to be a pure ISP, as the data still needs to be transferred off-chip and out of the storage section. This might bring up a new bottleneck. Also, in terms of physical design, it is rather bulky as it hosts two separate subsystems. Here on the right side, you can see a schematic of such systems. Also here, you can see an example of a Samsung Smart SSD that uses this approach to implement ISP. It includes a regular SSD subsystem coupled with an FPGA as the ISP engine. The third approach is to build a new integrated design that not only hosts the SSD controller, but also a dedicated processing unit for ISP engine. This design is the actual in-storage processing, as the processing engine is on the same chip as the controller. And since there is a dedicated unit for ISP, there will be no degradation in SSD's performance. On the other hand, such solution is harder to design and implement. As you can see in the diagram, both ISP engine and the controller are connected to the same on-chip data bus, which gives the ISP a much higher access speed compared to off-chip counterparts. In this section, we're going to go over our design for Solana. Solana is a high-capacity storage drive, 12 terabytes to be more specific, with additional processor for ISP. Solana is designed on E1.S form factor that is a standard enterprise and hyperscale form factor. The board is mostly occupied by NAND chips, some DRAMs, and the main controller chip that hosts both controller and ISP engine. This figure shows Solana's overall architecture. Solana is equipped with a custom-designed ASIC that is developed indigenously by NGD Systems. It has 4 ARM M7 and some controller IPs for the SSD section, and a quad-core ARM A53 for the ISP engine. The configuration is divided to three major sections. The front end that hosts the NVMe communication and data packetization and depacketization modules, and an ARM M7 core. The backend that deals with the flash chips and has several subcomponents such as 3 ARM M7 cores, fast release buffers, and error correction units. And finally, there is the ISP engine that has a quad-core ARM A53 and a full software stack that enables us to run operating system inside the storage. All these subcomponents are connected to the main database that gives access to a shared 6 GB DRAM and the host interface. On the software side, we have developed a fully indigenous SSD controller that takes care of all major storage functionalities, such as read and write, garbage collection, wear leveling, and etc. We have also developed a complete software stack for ISP that enables us to run a Linux operating system inside the storage. Currently, we have an Ubuntu 18.04 and 20.04 developed. Just like the host system, the OS can have access to the files stored on the flash to read or modify it. This dual access to the same data raises another challenge, that is the file synchronization and coherency check. To address that, we have developed an Oracle Cluster File System, or OCFS2, which is a shared file system that is developed by Oracle. We have also developed a tunneling system to give user access to the operating system that runs inside the storage drive. This TCP/IP tunneling communication over the NVMe channels assigns a unique IP to each ISP. Users can simply SSH from the host system to multiple ISPs and run their applications. To test our CSC design, we assembled an AIC storage server with an 8-core, 16-threads Intel Xeon Silver CPU that runs at 2.1 GHz. It has a 64 GB DRAM and can host up to 36 E1S drives in the front bay. Since Solana has a capacity of 12 terabytes, such server gives us a total capacity of 432 terabytes on a single 1U server. On the application side, we chose 3 NLP applications to evaluate the system's performance for distributed processing. These applications are speech-to-text conversion, movie recommendation, and Twitter sentiment analysis. Since there is no equivalent of Solana in the market, both in terms of capacity and availability, we had to choose our base system to be the same server with 36 Solanas, but as a regular SSD. Before going over the tests, let's have a quick look at the options to distribute the processing over several computing nodes. The first method is called model parallel and essentially means that each compute node is responsible for a portion of the computation on one model. Example of cases where model parallel can be useful is proper pre-processing of data, or table lookups on slower machines in terms of computation, or dense computation on faster machines. Note that in a model parallel setup, the synchronization matters a lot, since a halt on one part of the system will propagate to all other subcomponents as well. The second method is called data parallel, where unlike the model parallel, each machine has a complete copy of the model or application and can run independent of the other machines. Each machine gets a separate input and process it. So based on the application, synchronization might not be that big of a deal. But still, we have to make sure that each machine has enough input data to keep it running and increasing the overall utilization of the system. For our experiment, we're going with the model parallel, as our applications are small enough to fit on the 6 GB DRAM of each ISP. To efficiently deploy the application, we need to have a scheduler to keep track of all nodes' activities and assign new data to each finished node. This scheduler runs on a separate thread on the host node to be more responsive. It assigns a fresh batch of input data to each node and checks every half seconds if any of the nodes are done with their batch, and assigns a new batch accordingly. To release the CPU, the scheduler thread goes to deep sleep and wakes up periodically to check the status. This parallelization is asynchronous, which means if one of the computing nodes stall for any reason, the rest will continue with processing their portion of the work and deliver the result. One more thing to consider is that the processing power of CSDs with ARM cores and the host with Intel Xeon are not the same. For that reason, we chose a ratio of about 1 to 20 for the batch sizes of CSC and the host. This ratio depends on the application and will be computed at the beginning. Our first test is on the speech-to-text application. It is developed based on WASC, an offline speech recognition toolkit. We use the LJ speech dataset that has about 13,000 short audio clips with a total of 24 hours of speech and about 225,000 words. The figure on the left side shows the individual nodes' performance for different batch sizes. It shows that the node's performance does not change much with increasing the batch size, and also the host to CSC ratio is about 20. The figure on the right shows the overall system performance in terms of processed words per second. It shows that the host alone can process about 100 words per second, but adding 36 CSDs increases the speed to about 290 words per second, which shows up to 3.1 times increase in the processing speed. The second application is the movie recommender. It gets a movie title and returns the top 10 similar movie to that title. Each movie is represented by some metadata such as title, genre, director, cast, and storyline. Our movie recommender uses a cosine similarity to generate a similarity matrix and returns the top 10 closest title to the inputs. The dataset is a movie lens dataset with more than 58,000 titles and 27 million ratings. Same as the last test, individual nodes' performance does not change that much, at least in case of the CSD, and the ratio here is about 1 to 21. Performance measurements shows that by adding 36 ISPs, the overall processing speed increases by up to 2.8 times. Our final application is the sentiment analysis app. It was developed based on Python's natural language processing toolkit and was trained on the labeled dataset of 1.6 million tweets. It gets a tweet as an input and returns whether it has a positive or negative sentiment. Unlike the other two applications, the performance of sentiment analysis changes a lot by changing the batch size. We believe the reason is that it has rather light computation and thus, using higher batch sizes can better utilize the processors. However, there is a drawback in using large data batch sizes, and that is that the average latency for processing a specific input can increase. That is because when an input data is assigned to a node, it has to wait for all other prior data in the same batch sizes to be processed. And having large batch sizes means that the last part of the data will face a high latency to be processed. The right figure shows the results based on the batch size. And it also shows that adding the ISP can increase the performance up to 2.2 times compared to the host alone. To measure the power and energy consumption, we used a power meter to measure the overall power of the system. Based on their measurements, the standalone server consumes about 167 watts in idle mode. When we add 36 CSDs with disabled ISP engines, the power consumption rises to about 405 watts, which gives an average of 6.6 watts per drive. When running the application with disabled ISP, the power consumption goes up by 77 watts to about 482 watts. And when engaging the ISP engine, it increases for an additional 10 watts for 36 ISPs. That is an average of 0.28 watts for each ISP. The figure on the right shows the average energy consumption per query for different applications and with different number of engaged ISP engines. For instance, the energy per query for movie recommendation goes down from 832 joules per query to about 327 joules per query with 36 CSDs. This figure also shows the normalized energy consumption based on the standalone host setup. As you can see, the best reduction in energy is for the speech-to-text application with about 67% enhancement, which is partly for the added processing speed and partly for the reduction in data transfer size. And this table summarizes our test results for all three applications. To conclude this presentation, we have introduced the world's first E1S computational storage drive called Solana, which can be used both on edge systems and data centers. Solana can augment extra processing power to the system. The ISP technology that comes with Solana can be easily deployed as it has an operating system that enables users to run applications with zero changes. It can be utilized to run applications in parallel and improve systems performance. Based on our results on the three NLP applications, it can enhance systems performance by up to 3.1 times at zero extra cost by deploying 76 CSDs on the server. And it can reduce energy consumption by up to 67% depending on the application. In our future works, we are planning to develop the next generation of CSDs that will have more powerful processors, embedded accelerators such as neural engines, and higher DRAM and flash capacity. We will also investigate the possibilities of developing a data-aware distributed system that can benefit from the temporal and spatial locality of data, and can also be used for general-purpose applications. Thank you so much for your attention, and if there is any question, I'll be glad to answer.